This is your host for Baji the Handsome Cat, where we also speak about physics, astronomy, cosmology, astrophysics, and lately planets and planetology. I am back for my second and longer live tonight. We usually start a bit later at night. If we're starting at night, I've been starting something like 10:30, 11 p.m., sometimes midnight. But here we are, a little bit early this time. Actually wanted to go live and then stay live for a longer period of time today. But instead, I did a short live this afternoon where I was preparing for this particular live, and I have the materials ready for you to cover today and tonight. And in the middle, I did a little bit of self-care, and that took a little longer than I anticipated. I ate a rather large dinner, and I did some home exercises, and now I'm feeling much better and happier, and I'm just put on some lotion as well on my hands, which are very dry because it's very cold here in Boston. It's been it snowed a lot last night into this morning, so I did a snowy live. If you are interested in seeing the snow on the ground and how much of it there is or there was, actually still is, because it's incredibly cold, it will probably stay on the ground for a very long time. Then I showed that in my previous live, and you can go check it out. But yes, we're live. Welcome to the live. If you're joining, oh my gosh, I forgot my iPad. I'm gonna have to go get it. That's where I'll share the live. But thank you so much for joining. Welcome, 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 welcome everybody for joining. Welcome to the live. And if you're seeing this as a video upload later on, then also welcome. And thank you in advance for leaving any comments on the live video. It really helps me out, and also later on I have a lot of fun reading your comments on the live that I just did. So Heike, thank you so much. I've been reading your comments. I love that you leave so many comments. It really helps to add keywords and metadata, I believe, to the video as well. So thank you so much. Hector, hello Hector, how are you? Ooh, and thank you for liking the live, yay! Thank you for liking the live. Thank you so much for liking the live, yay! Thank you, thank you, thank you. I'm trying to get 30 likes today if I can. So 3 likes done, yay! Thank you for being here. Welcome to the live. Hector says hi, hi. Zach Efron says, hi, what's up? How are you? I'm good. How are you? How are you? Johnny Boy says, hey, remember me? I don't think I remember you, but welcome to the live. How are you? Slim Shady says, just like, thank you so much for liking. Thank you, thank you, thank you, thank you, thank you. Thank you for liking the live. Really appreciate it. And I'm moving my stuff so that I can bring my notes over this way. Thumbs down, says Sean Banks the trucker. Oh no! Oh, the Phoenix Dragon says hi, hi. Hector says, what time is it? It is 9:32 p.m. I look at the microwave naturally, but the microwave is a little ahead. Zach Efron says, what is this stream about? So we're going to be talking about exoplanets. So I have an agenda. We're going to be talking about exoplanets, novae and supernovae, and our galaxy. And we're going to be referencing a book that I will share with you soon here. Thank you. Thank you for liking. Slim Shady, hope you have a good day, ma'am. Thank you, Slim Shady. How are you? B&B Brunch. B&B Bunch says, I like and subscribe. Thank you. Tian Tran says, hi, hi. Hello. Phoenix Dragon says, same. Hello. Kinley the Animals Girl says, I just like, thank you so much for liking. Yes, please do like and subscribe and share. And if you could share the live with anybody who you think might be interested in the live and the content, we're going to be talking about astronomy soon here, and we also hang out with kitty cats. Sometimes they also feature in the lives, so that's what this live is about. Hi, do you think Encanto is a good movie? Andrew B, this is for a survey. I haven't watched it, Zach Efron, so I don't know. I haven't been able to watch a lot of movies lately. Actually not caught up on any of the recent movies that might have come up, actually. So I don't know. Phoenix Dragon, does anyone know FNAF? I'm in your walls. How old are you? Okay. Well. I got 6 likes. If we could get to 10 likes and then 20 and then 30, that would be amazing. And I'm gonna go get my iPad. It's like right here, but give me a second because I wanna share the live. Hi Tien Tran, thank you for that message. It's a little unreadable, but thank you. Okay, so today we will talk about exoplanets. Now, as you know, or might not know, if you're new to the channel, which is also totally fine, we have been talking a lot about the planets in our solar system. And in fact, the planets in our solar system themselves have a lot of diversity, and they help us to learn potentially about exoplanets as well, which are planets in different star systems outside of our own solar system. Oh, nice. Hector says you have 7 likes. Thank you so much for 7 likes. Yay. Can we get to 10 likes? Yes. Can we get to 10 likes? Thank you so much. So even the planets in our own solar system display a lot of diversity and variety. And of course, depending on the planet's distance from... Oh, thank you. Hi, Peter. You hope so. What do you hope for? So depending on the distance the planet is from the sun, it tells us a lot actually about the evolution of our solar system, the formation of these planets. And we have been at length kind of talking about various planetology types of things and comparative planetology to help us with understanding how planet formation happens and how our solar system itself has developed and evolved. And now this is very important for us to understand, especially as it relates to other star systems, and it helps us with kind of preparing ourselves for things like exoplanets, because just even our own solar system giving us all this information and things to learn about the different planets help us to kind of ground ourselves in what we might expect for other star systems as well. So I'm looking for the chapter as usual. Oh, here it is. Thank God. So sometimes I go right past it, but here it is. So, okay, so we are using, I will say just a caveat that my background is in particle astrophysics, so planets is not exactly my exact specialty, but we are using this very amazing book, which is a textbook for astronomy and astrophysics for majors used in a lot of schools, and the authors of this are Barbara Ryden, Bradley M. Peterson. Both are professors at The Ohio State University, where I went to grad school. And this book is called Foundations of Astrophysics. So we use this book as a reference a lot, and especially for the planet stuff, we've been finding it to be very useful. How can we reach an exo so far? So that's a great question. If you're interested in the exoplanets and how we research exoplanets, even though they're at such a big distance away, some of the challenges with finding exoplanets and, seeing them and things like that are exactly going to be the topic of discussion today. So exoplanets, of course, as you pointed out, even just other stars that are not our sun, even the closest one are extremely far away. We actually talked about other stars and properties of stars a few lives ago. I think it was maybe Saturday afternoon that I talked about that, where we discussed how far these other stars are. And of course, when it comes to finding the planets that are in those other star systems, that's actually a whole nother type of challenge, because planets are, of course, not as luminous as stars are. So indeed, you will see that there's a lot of challenges with that, and we will kind of see how to navigate that. But also, prepare yourself for certain surprising and startling results when it comes to our findings of exoplanets so far. There may be some very interesting facts here that we talk about today. So prepare yourself and hope you enjoy. And yes, thank you so much. And now I will share the live because it became really quiet and hopefully more people can join. Welcome, welcome. Thank you for joining. Hello, welcome, welcome. Thank you for joining. We're just getting started and we will be sharing the live and we will be talking about exoplanets first today. Okay. Okay. Yay. So there will be certain measurement techniques that we will talk about when it comes to the exoplanets, which will hopefully directly address what Combat is asking about. So thank you for that question. We will definitely try to address it. And also remember that one of the big motivations for finding exoplanets is, of course, to I'm in a hurry. Oh, thank you so much. So one of the biggest motivations, of course, is to also find alien life, which is to see if there is other planets or other homes and worlds where life may have been supported, if they are something similar to us on Earth, for example, or even may have certain sort of evidence of having, say, liquid water at some point. So there might have been life at some point, because not everything has to be happening in the same timeline as us in our contemporary. For example, Mars used to have liquid water. There is some evidence of erosion from liquid water on Mars, which means that at one point it had liquid water and may have been able to support life, but currently it does not. So keep that in mind as well as we learn these things, because not everything has to be happening sort of co-located in time with us, right? So just like we are, the human civilization has developed here on Earth at this particular timeline. The Earth is a very suitable home at this time. But a long time ago, the Earth's atmosphere was more similar to the atmosphere of Venus and had more carbon dioxide in it. But then our distance from the sun is so nice that we are able to have water in liquid form. In fact, we have oceans of water in liquid form, and these oceans actually absorbs the carbon dioxide from the atmosphere and turns it into limestone. So because we captured carbon dioxide, which makes the atmosphere poisonous and kind of toxic for life, and turned a lot of it into rock, we are able to convert this atmosphere to be better. And then plant life developed, and plant life also converted a lot of the carbon dioxide to oxygen. So the stuff that we did on Earth, for example, using the fact that we have liquid water, has greatly changed the atmosphere for the better for life and made it more breathable. Unfortunately, that did not happen, for example, in Venus, which is a twin planet for us. It is much like Earth in size and mass, but it has it's a lot hotter. It's over 700 Kelvin in temperature, and it's closer to the sun. But again, it's very similar to us in mass and size. And it has an atmosphere, which we have an atmosphere, and a lot, certain planets, certain other planets don't have an atmosphere. Mars does not as much, and then Mercury's is very transient because it's too close to the sun. Any atmosphere it has is really solar winds getting trapped for a little while, and then it's kind of too hot on Mercury, for example, right? So not every planet is going to be very suitable, very life-friendly. We are even looking into certain moons of other planets, but let me finish up this thought, which is that, Earth and Venus, so similar in many respects, but so different. One can host life and one cannot. So if, by some miracle, Venus was able to convert its carbon dioxide to, say, something like rock and make its atmosphere more breathable, then Venus could host life. But so far, we don't really think that has ever happened. It's still the way it is. But even Earth was not always so friendly towards life. And similarly, when we search for exoplanets, or even learn more about the other planets and the moons of the other planets, even in our own solar system, such as Europa, we think has oceans of liquid water in the subsurface, and the surface of Europa looks a little bit like our Arctic region. We talked about this in the past as well in these recent live streams. We talked about our own planets in the solar system as well as the moons of these planets. And of course, we first talked about the rocky metallic terrestrial planets: Earth, Mars, Venus, Mercury. These are what we call the rocky, metallic, or terrestrial planets. These are closer to the sun. And then we have the farther away stuff that's much bigger in size planets, or what we call the Jovian planets, or Jupiter-like planets, including, of course, Jupiter, Saturn, Uranus, and Neptune. And Jupiter, as I always like to say, it belongs to a league of its own. Most of the other planets are nothing really like Jupiter. It's really massive, much, much more massive than all the other planets. At 318 times the mass of the Earth is the mass of Jupiter. So, we talked about those. We saw how Jupiter and Saturn are a little bit similar. So we talked about them sort of in a group. Then we talked about Uranus and Neptune, and those were sort of in a group, and we talked about those. And importantly, these planets also have a lot of moons, and these moons itself are actually very active research topics. So stay tuned. We will learn more. Are we sure there was never any living in Mars? I don't believe... NASA had once thought of building a colony on the moon using subterranean caves below the surface. Yeah, so I'm not sure that we know that there definitely wasn't life. There could have been. They're supposed to be making a hydroponic dome on the moon. Hey all, hi Steven. So yeah, let me say hi to everybody real quick. Hi Peter, hi Combat Sports, hi Harper, hi Steven, Peter. Okay, great. Yeah, so we know evidence of erosion by liquid water on Mars, and we currently know that there's erosion by some wind on Mars. So we know about that. We don't know that there was not life on Mars. There could have been. I don't know. I think Mars is definitely an active research area. We covered Mars in some more detail in one of the live streams in the last few days. So we covered, Earth, our moon, Venus, Mars, Mercury, and then we moved on to the Jovian planets, and we talked about Jupiter, Saturn, Uranus, and Neptune. So this type of planetology, I might real quick cover planetology for you guys, because I think some of you here were not there for the planetology discussion, because pretty much after learning about all the planets in our own solar system, you start to see the diversity and variety, even in our own solar system. And by the way, another thing we learned is that, look at our solar system. The biggest planets, Jupiter and Saturn, are sort of towards the middle of the solar system. Right? And then we sort of see this similar thing happening in sort of tiny mini solar systems, which are not really solar systems, but we call them the Jupiter system, and Jupiter and its moons, or Saturn and its moons, or Uranus and its moons, are kind of like almost like tiny little model of solar system with a warm body or object that's bigger or massive, and a bunch of satellites around it. And there too, we find that the more massive or the most massive moon is sort of towards the middle of the system. And we saw that that was because somewhere in the middle of the system, there is a favorable trade-off between temperature and density. Temperature as in cool enough for volatiles to condense, and density high enough to make massive bodies. So the most massive moon of Jupiter, for example, Ganymede, is sort of towards the middle of the system from Jupiter Saturn's Titan is sort of towards the middle of the system with Saturn, and Uranus's Titania is sort of at the middle of the system with Uranus, and Jupiter and Saturn are sort of at the middle for our solar system. So these, comparative types of learnings that we have been learning and gleaning from the information from our own solar system and our moons are extremely important information to keep in mind when we move forward into exoplanets, okay? So just keep that in mind. Let me share the live. Thank you everybody for being here. If we ever land people on Mars, we will have to look for evidence of life on Mars, but in the distant past, it could have happened. Is to try to, yeah, well, I mean, we can see more information from the rover too. Keep in mind that that Mars is an active research site. We are currently and have been spending money to research Mars. Of course, the rover is there and other things are there. So, sometimes it takes time for all this instrumentation to collect the data, and then we also have to analyze the data and then release it to the public, right? So there can be a lag in what they're finding and what we're finding out as the public. So give it some more time. There very well could be information coming from Mars that is also very interesting. So, and that's what I mean, is that you'd be surprised sometimes at what you find when you look. So, for example, the fact that we found subsurface oceans on Europa, maybe. So Europa is another very active research site where we are very interested in understanding Europa better. First of all, Europa is very far away. The planet Jupiter is 5.2 astronomical units away from the sun. We are at 1 astronomical unit away from the sun. So you can imagine Jupiter is 5 times more the distance away from the sun. And so its moons that are going around Jupiter are obviously sort of at that distance too. And so this is quite far. So it's not so easy actually to know every detail about something like Europa. Even Mars. Mars is one of the rocky inner terrestrial planets, but even Mars is kind of far, right? So it's not like we can just obviously know everything about these planets, even the ones that are in our solar system itself. So we have to have some patience with understanding more about them and understanding the results that come out of these things and doing the research and supporting the research to learn more about the planets, because it's not so easy. I mean, do we even know everything about the Earth? We live on the Earth, right? So we have to be patient and continue to support these efforts. Otherwise, it's pretty impossible, right? So, okay, so some of the comparative planetology within the solar system stuff that we talked about, I wanted to recap for you real quick because I think that would be very beneficial for the exoplanet discussion. The theory is try to land a team on Mars. It could happen with the rover by chance too. Yeah, so, the moon is another good site. I would say continuing to understand the Earth is a good idea. I mean, the Earth is really big. If you fly from one side of it to the other, you really get a feel for that. Like, so I'm from India. When I fly to India, I'm really reminded and a little bit humbled by the fact that the Earth is not a small planet. It's very big. And so just imagine something like Jupiter, Saturn, Uranus, Neptune. Not that those planets are very habitable, but these are very, very big. Okay? So, surfaces of planets are shaped by competing internal mechanisms and external mechanisms. So I just wanted to give you the highlights of the comparative planetology and sort of remind ourselves what these highlights kind of mean without, getting into it too much. So for example, we talked about, especially for the terrestrial planets, we talked about how there is volcanism and impact craters from the heavy bombardment period. So there was a period in our solar system of what we call heavy bombardment, where smaller objects and planetesimals were basically hitting every object and creating these impact craters, some of which are, of course, very evident on the moon and some other objects as well. These are actually pretty common. But then what happens is that certain objects have a lot more volcanoes happening. For example, even Earth has a ton of volcanoes. And volcanism is something that can actually repave or pave over these impact craters. So objects where a lot of volcanoes happen all the time because of just being geologically active or because of the environment they're in, will actually may have less impact craters because whatever impact craters they might have had are sort of paved over by the volcanoes. So this is a very interesting thing that we saw throughout our solar system. So Earth has volcanoes, and let's just read this real quick. The larger planets, Venus and Earth, have surfaces on which volcanism and erosion. So the other thing that can happen too is erosion, whether that's with water for us on Earth or wind or whatever, rain, etc., right? So water or wind erosion. So Venus and the Earth have surfaces on which volcanism and erosion have all but obliterated the evidence of the early bombardment era. The smallest planet, Mercury, has surface features that are primarily the result of bombardment early in the history of the solar system, with little modification by volcanism and erosion. Mars is the intermediate case. So Mars is a very intermediate, nice planet that gives us sort of both. So it's almost like Earth is perfect, Venus is too much, and Mars is sort of a little less than perfect, but workable. Not having a poisonous atmosphere is a really good case, of course, for Mars. It's not as good or nice as Earth. I will just tell you that now, so that you're not very disappointed when you go there. Okay, but it does have rock, and it's pretty good. It's not too bad, not too hot. Of course, colder than the Earth. Even a summer day on Mars is going to be a little chilly, but at least you're not instantly dying from the breathing of the carbon dioxide too much. So the smallest planet, Mercury, has surface features that are primarily the result of bombardment early in the history of the solar system, with little modification by volcanism and erosion. Mars is the intermediate case, with ample cratering in some locations and large volcanoes in other locations. So Mars gives you that diversity, ample cratering as well as volcanoes. So we know that, oh, okay, yeah, sure, those both happen. And there's ample evidence for past erosion by water and current erosion by wind. So this is what I was talking about. There's ample evidence for Mars to have had erosion by water, liquid water, as well as currently erosion by wind. Okay? So these types of things, like what I just mentioned, erosion, cratering, volcanoes, these will heavily affect the surface features that we see for the planets. And not only that, I will mention real quick that even something like the moons of Jupiter are very much affected by something like their distance from Jupiter. So when you're very close to Jupiter, you experience a lot of tides, and even the insides of the closest moon of Jupiter are basically going through tidal forces and disruptions, and there's a lot of volcanoes happening on that particular moon. It's called Io, for the Galilean moon of Jupiter. So things like that. Hi, Doril. The next point is that more massive, colder planets are better able to retain atmospheres. So this is another thing. Whether or not a body can retain atmosphere and the chemical composition of the atmosphere that it does retain depends on the competition between atmospheric temperature and gravity. If you have something that is, moving really fast and your gravity is not very strong, then that thing that's moving very fast, such as gas molecules of some material, can leave your atmosphere, leave your planet, and be lost to space. So it's both about gravitation of the planet, so how massive the planet is, and also about the atmospheric temperature, because atmospheric temperature is nothing but the sort of how fast the things that are in the atmosphere are moving, right? So, okay, so real quick, more massive planets, all other things being equal, have higher escape speed. So this is escape velocity to escape the gravitation of that planet, of course, have higher escape speeds and are better able to retain an atmosphere at a given temperature. The lightest atmospheric particles are moving most rapidly and are the most easily lost to space. In order of increasing mass, consider an array of objects within the solar system. So now we will look at a few specific examples. Okay, so Pluto is extremely cold. So Pluto is a dwarf planet. It's not a planet, but ooh, thank you for the likes, by the way. Can we get to 20 likes? Thank ya. Pluto is extremely cold with a temperature of around 50 Kelvin at perihelion, for example, but it is too low in mass to retain anything other than a thin methane atmosphere. So on Pluto, that's what you'll breathe, a bunch of methane. The moon, which is our moon, is more massive than Pluto, but it is too hot at the subsolar point to retain any atmosphere at all. So for the gravitational pull of the moon, it's not cool enough to retain an atmosphere. Mercury is too low in mass and too hot. So Mercury is too low in mass as well as too hot to retain any substantial atmosphere. Sometimes it has some stuff from solar winds, transiently on it as an atmosphere. Mars, that's what we were just talking about. Mars is cool. So if you like the cool weather, be my guest on Mars. Mars is cool, has a temperature of around 290 kelvins on a warm summer day. So bring a jacket and go to Mars. It will be nice, but its mass is too small for it to retain anything more than a weak carbon dioxide atmosphere. So again, not much of an atmosphere there other than the weak carbon dioxide atmosphere, but maybe you can bring oxygen tanks or just hold your breath and wear a jacket on Mars. Otherwise, very nice, very rocky, very rusty. If you like the color red, you will be very happy on Mars. Next is Venus. It's too hot, but it is very much a good mass enough to retain a very substantial atmosphere. So Venus is 740 kelvins, but it is massive enough to retain a thick carbon dioxide atmosphere. So the thing that is a thick carbon dioxide atmosphere on Venus is a thin carbon dioxide atmosphere on Mars. So if you bring your oxygen tank, hold your breath, wear a jacket, should be fine. And yes, it will soon be a part of the US. Yay! About time. No need to dilly-dally that. The Earth is, of course, warmer than Mars. Very nice. Earth will be like Hawaii soon, and all the people can go to Mars, and they can come to Earth for a vacation and boom the economy here. So the Earth is warmer than Mars, but it is massive enough to have retained a dense carbon dioxide atmosphere initially. So this is what I was talking about, because we were able to convert carbon dioxide to limestone, and later on evolve the atmosphere to have more nitrogen and oxygen because of plant life. Earth is perfect. Yes. So it's massive enough to have retained a dense carbon dioxide atmosphere. Initially, this evolved into a thinner nitrogen and oxygen atmosphere because of the presence of liquid water, which removed the carbon dioxide and plant life, which added the oxygen. So that's about Earth, my favorite planet. Not that I have strong feelings. The Jovian planets are sufficiently cold and massive to retain thick atmospheres of hydrogen and helium. Now, we have talked about how the Jovian planets, of course, are very different in what they retain and what they're just made of in general, because remember, they would have condensated at a very different distance away from the sun, at a larger distance away from the sun. So the condensation for the initial formation of these planets would have happened at lower temperatures. So they're made of materials that do condensate at these lower temperatures. But these are very massive planets. So they're definitely massive enough and cool enough to pretty much hold a lot of atmosphere. And generally speaking, they have thick atmospheres of hydrogen and helium. We will see that actually Jupiter has a very big layer of metallic hydrogen within its composition. So that's another important fun fact about Jupiter. And of course, it has just hydrogen generally as the outer layer. You have strong feelings for Earth. I said I don't have strong feelings, but I do like the Earth as our planet. She only loves the Earth. Where is everybody today? Why are not more people joining this live? 13 likes. Thank you so much. Please do like the live. I would love to get 15 likes. No, 20 likes. How is 20 likes? Oh my God. Astronomy is good. Wow, you guys all know each other now. Look at you, all 6 of you are friends. We need James. Agreed. In a different way than you were thinking, but you want the James that comes here and makes trouble. Stephen, I guess we can both be astronomy Batmen. Batmen! Aww. Reese! Hi! Hello, Reese. Hello, Batman. Hello, Doral. Hello, Stephen. Hello, the moon landing guy or girl. Hello, Batman. Hello, Doro. Hello, Stephen. Hello, Reese. Stephen is an astronomy Batman. Stephen is the only one who is supportive of astronomy. Everybody else is just being a troublemaker. You're always listening, but she doesn't love you. However, you need to know I don't either. What do you mean? You don't listen to all the fun facts about astronomy? Ah, Steven says, I think of you guys as friends now since we seem to enjoy the lectures. Yay! Thank you, Steven. More like it. And she's my... I used to be supportive, but your chat is just so dang fun. I said I don't love Batman. Oh, yeah. Well, I mean, I think you guys are supportive by being here, and as soon as I see a fight breaking out in the chat, I'll just ignore it because it'll be too distracting for me. I'll forget all about the planet stuff that I wanted to talk about. I know a bit of astronomy. Thank you. Very nice. Okay, I'll continue. So I talked about how, okay, the next point is giant satellites of Jovian planets show patterns consistent with our ideas about the formation of planets. So this is where I was saying how the largest planets in the solar system are sort of towards the middle of the solar system, like Jupiter and Saturn. And the same thing is true for the moons of Jupiter and Saturn, where the largest moon of Jupiter, which is also the biggest, largest giant moon of the solar system, Ganymede, is sort of towards the middle. Same thing with Saturn's Titan, and same thing with Uranus's Titania. Lesson number 4, or fourth point about this comparative planetology, is that many unusual features of the solar system can be attributed to giant impacts. So this is the thing I was saying, that there was this era of giant impacts, an era of heavy bombardment, and that led to certain things. And we even talked about the theory of how the Earth and the moon came to be, or the moon at some point became our moon. And we do think that the Earth and the moon suggest histories that are quite different. So the Earth and the moon don't have the same histories, don't have the exact same composition, and there are certain things that we've gleaned from that as well. But it's kind of specific to the Earth and the moon. Okay, so after this, we can, I think we're very close to being able to start the topic of exoplanets. Let me just make sure I didn't miss any important remarks by you guys. Read the fight out loud. Batman works alone. You better appreciate us. I do. Pulls out my freeze guns. Oh, that's right. Reese, you missed the earlier live today where Steven said something harsh. Steven, who never says anything harsh, said something harsh. So Steven, do you want to repeat it so that Reese can hear it? Dr. Freeze, I didn't forget. I just can't read. Reading is overrated. Dora, can you stop? Don't encourage Batman. Steven, yes. Steven said something about, oh my gosh. Actually, now I don't want to repeat it. Now I don't want to repeat it because it will bring back that whole topic. I want to you know, I feel like Batman should feel a little bit more unsafe. I think it's good for Batman to feel a bit less comfortable and safe in this chat. Doro, if you want to make him uncomfortable. Oh, there we go. I'm so sorry. Now the chat has less people. There you go. Reese, 1.8 thousand seconds? That's too much. Do like 10 seconds. I need the watch hours, guys. Are you serious? We can't. Oh my god. Where the frick did he go? I'll try to bring him back. Oh my god. There. I put him at 10 seconds. Batman, you can come back in 10 seconds after you've learned your lesson. Now I'm losing my pen. Batman. Batman, you were timed out for 10 seconds. Can you stop being important? Maybe just say nothing for a while. He's like timed out for 10 seconds and then he's like, I don't know what's going on. Can someone catch me up? You were being weird and so Doro timed you out and then Reese upped the time. Gosh, why do I even look at the chat? You know what? From now on, I will not look at the chat. Why do I even bother with the chat? What are you sending, Batman? Stop it. Stop being important. Batman, sit quietly for the next 45 minutes. James and Grimm is illegitimate. All right, everybody. We will now talk about the origin of the solar system. Just a few more fun facts before we go on to exoplanets, okay? And Batman, just say nothing for a while. Just listen. Just listen to the lecture. Say absolutely nothing. And don't make yourself important. You are distracting everybody. Our understanding of the history and evolution of the solar system is still incomplete. So there are still mysteries to be solved about our own solar system, but a comprehensive, self-consistent picture has begun to emerge. Our mental picture of the solar system, forming from a rotating protoplanetary disk, explains many of the basic features of the solar system, including these points. So planetary orbits are all in nearly the same plane. The sun's equator lies close to this plane. Planetary orbits are nearly circular. Planets all orbit in the same direction. Most planets and the sun, so not all, but most planets and the sun rotate in the same direction as the planet's orbital motion. We have also noted that although the sun contains 99.8% of the mass in the solar system, it contains less than 5% of the angular momentum, which I was thrilled about. It was amazing. The planets represent the material in the pre-solar nebula. So because we all come from a gas cloud or nebula that ultimately condensated to become the sun and the planets, so whatever angular momentum was in that nebula has been inherited by us, all of us. Okay, so most of the mass went to the sun, which is of course humongous compared to everybody else in the solar system, but the planets represent the material in the pre-solar nebula that had too much angular momentum to contract into the sun as it was forming. So the sun was like, leave me alone, angular momentum. I'm gonna be huge, massive, and not do too much in the sense of getting angular momentum. Let the planets be less huge and rotate and conserve the overall angular momentum. Okay, so then, we kind of left off at this part. So the next part, we are now done recapping the few lives that lead up to the stuff that we're about to talk about. Oh my God. So we have now recapped the lives leading up to the next part that we're going to talk about right now. And this part will lead us to exoplanets. So get ready for that. Okay. All right. Nature of small bodies. in the picture we have developed, comets are primitive bodies, planetesimals left over from the first phases of formation of the solar system. Asteroids are a mix of primitive planetesimals and fragments of larger, differentiated bodies that were broken up in collisions. Some of these bodies have been captured as satellites by planets. Other satellites, particularly larger satellites, in prograde, equatorial, nearly circular orbits, were probably formed at the same time as their central planet, mimicking on a smaller scale the formation of the solar system as a whole, like what we think about Jupiter and its moons, for example. Small debris in the solar system is replenished from comets and asteroids. Otherwise, the Poynting-Robertson effect would clear out the solar system of these small bodies. Thank you, Stephen, and the rest of you. Can I get 20 likes, please? Okay. So next we will talk about differences in chemical composition. Ooh, thank you for the like. Thank you for liking the live. 20 likes would be amazing. So some differences in chemical composition is to be noted as well. Thank you, Stephen. The broad chemical composition differences within the solar system reflect the temperature gradient within the protoplanetary disk. Oh, yes. So remember how the stuff that will condensate closer to the sun where it's hotter is going to be different materials than the stuff that condensates farther away from the sun where it's cooler. So intrinsically, the compositions will be different. What? Okay, the inner planets are primarily composed of the least volatile substances. The outer planets were able to grow to larger sizes because volatile ices could condense at the lower temperatures found in the outer disk. The combination of icy, rocky, and metallic planetesimals let the outer planets grow to a sufficiently high mass to retain hydrogen and helium, the most abundant elements in the pre-solar nebula, in their atmospheres. So just like in the universe, so once again, remember how the most abundant element in the universe is hydrogen. So the pre-solar nebula, the most abundant elements in the pre-solar nebula is also hydrogen and helium. But guess what? A lot of this is in the Jovian planets. So, and that's all because of where it is and where things condensated. So the combination of icy, rocky, and metallic planetesimals let the outer planets grow to a sufficiently high mass to retain the hydrogen and helium, which are the most abundant elements in the pre-solar nebula in their atmospheres. So it's there, but if you're don't have enough mass to then retain those lighter elements, then you're going to lose it to the space. Basically, it will evaporate away to space. Thank you for the likes. So presolar nebula is the gas cloud from which we all came. And the most abundant elements in that presolar nebula was hydrogen and helium, much like the rest of the universe. And because of the condensations happening, which formed the sun and the other planets, but not every planet has the same mass and the same type of composition, the Jovian planets were massive enough and had enough of the icy, rocky, metallic planetesimals kind of combining lots of mass, and then they retained a lot of that hydrogen and helium as well. And remember how we talked about the layers within Jupiter, Saturn, Uranus, and Neptune, where Jupiter and Saturn even has a metallic hydrogen layer, a substantial metallic hydrogen layer, especially Jupiter. So that's one thing too. Rings around Jovian planets, that's the next point. All the Jovian planets have ring systems inside their Roche limits. The ring systems represent either bodies that failed to form because of tidal stresses, or bodies that were destroyed by tidal forces, or perhaps both. Next is chemical differentiation of the terrestrial planets. This is also something we looked at where the heaviest stuff kind of sinks to the center and the lighter stuff is up on the surface. And this is saying radioactivity is the key to understanding why all but the very smallest rocky and metallic bodies in the solar system are chemically differentiated. In the early solar system, radioactivity provided enough heat to melt iron in planetary interiors, thus precipitating a complete liquefaction of the interior and subsequent stratification by density. So all the things kind of chemically differentiating is something we see here on Earth and other places. So, okay. It has become an essential part of the stream. Okay, science quiz. Science quiz. You guys are making me lose my mind. It's 10:26 p.m. Science quiz. Shout out my cat. I like Jupiter and Saturn, but if everyone has ever seen it, Saturn has an octagon-shaped cloud formation at the North Pole. Hi, DR. Hi, Doro. Quiz. Let's do a quiz. So, name the biggest planets of the solar system. Go. Everybody try to, there's like 4 of you here. Try to name the giant planets of the solar system. So some of you have to name more than one because there's not enough people here. There are 7. The giant moons, Reese. Do you even understand English? The giant moons, the giant satellites of the planets, not the planets. Did I say planets? I'm sorry. Can you please name the giant moons of the solar system? The biggest moons of the solar system. There are 7. Yes! Those ones. Yes. Io is 1. Europa. Yes! Ganymede, you spelled it wrong, but sure. Ganymede. Let me make sure. Yes. Ganymede. Good job, Reese. Good job, Doro. So I see the 3 moons of Jupiter have been named. Io is 1. Ganymede is 1. Ganymede. Europa is 1. Titan. Yes. Titan is a moon of of Saturn. It's one of the largest moons. No, Stephen. Name the 7 largest moons. And one of the moons, I'll give you a clue. You definitely know one of the moons very well. So the 7 largest moons of the solar system, they're also called giant moons. We covered them in my live stream called Giant Moons. There are 7. So, yes, our moon is one of them. Yes! Yes! Our moon is one of them. You already named Ganymede, Io, Europa. So you named our moon, Ganymede, Io, Europa. Somebody said Titan. What else? How many Galilean moons of Jupiter? Stephen, you know this. So I think we've got our moon, Io, Ganymede, Europa, Titan. So we have 5. We need 2 more. Or maybe Stephen has one. Stephen, are you saying Triton? Triton. Triton, the giant moon of Neptune. Stephen said Callisto. Yes! Good job. Callisto is Callisto. That's the last giant moon of Jupiter. He Googled it. Stephen is a Googler. So yes, I think you guys got it all. Callisto, Callisto. He's got Google on speed dial. Aww. But yeah, it's our moon, Io, Europa, Ganymede, Callisto, Titan, that's the moon of Saturn, which is one of the giant moons of the solar system. And then Triton, which is the giant moon, which is a moon of Neptune. And we even talked about the potential future death of Triton, and it will just become one of the rings of Neptune, actually, because it's on a retrograde orbit around Neptune. So since you asked for a quiz, here it is. I gave you a quiz and you passed. You guys are actually really good at this. You're not bad. Not bad at all. Ooh, can we get 25 likes? That would be amazing. We have 22 likes at the moment. I had to think of the 4 big moons of Jupiter. Yes, the 4 big moons, Io, Europa, Ganymede, and Callisto. You guys have impressed me. I thought with all your stuff in the chat that you guys are not listening, but you are. Okay, so that was a pop quiz. Now we will talk about detecting exoplanets. Okay. What we're talking about is exoplanets. Actually, can I take a quick break? I need to take a quick break. I swear it'll be quick. Batman, you can talk to everybody else with your Batman, I'll give you a job since you failed the quiz. Batman, you've miserably failed the quiz. Here's something you can do in my absence. Harper, hello. Hello. So, in my absence, Batman, can you Google the definition of exoplanets and tell the chat about exoplanets? And keep on doing it. tell something new in every chat message about exoplanets, and I'll be right back. I'm going to put this phone on charge so that we're not interrupted when we do the exoplanets. Okay. I will be right back. Oh my gosh. Exoplanets. Somebody tell him what exoplanets mean. You make me happy when I watch. If you ever watch the movie 2010, Europa is discovered to be teeming with life. Oh my God. Oh my God. Okay, phone's charging. I'll be right back. And then we will talk about exoplanets. And everybody, be good. Don't make trouble. Be good. And Batman, you have an assignment. Google exoplanets and put something related to exoplanets in the chat right now. Is a planet orbiting another sun outside our solar system? Yes, another type of star. Exactly. Good job, Steven. 20 points to Gryffindor. Batman, you're really lagging behind. Contribute with exoplanet information. Puts on my behaving big boy pants. Aw, that's so nice. And if the exoplanet answers are not in the chat, that's true. Practice of juggling. Can you like the live? Can we get to 30 likes today? As long as she's not cat. Oh my god. Currently I'm putting some lotion on actually. It's dry. It's dry. When will James be here? You know, it's pretty early for him. Maybe he's not up yet from his Britain timings of the morning. I know that's what you are here for. It's not for the astronomy, for which I still don't see the exoplanet's answer. So, you know what would be good? If you could answer the exoplanet question instead of worrying about James. So, okay. All right. I mean Batman. Did he answer it? Batman was tasked with a job. Batman was tasked with a certain job, which was to talk about exoplanets while I used the bathroom and made a phone call. Excuse me. I drink a lot of water. Excusez-moi. I drink a lot of water. Who did you call? Shall I give you their number too? So you can call them? As long as she's not cat juggling. She called the plumber? Really? Don't say that. I don't want any plumbing. I will have excellent plumbing. Excellent. Ew. Batman, take a seat and shut up. Yay, I love that you're happy. I'm happy. I'm happy. I'm happy. I'm happy. I'm happy. Plumber. Plumber. I am happy. Why are you so pretty for real though? Shh, sit down and zip it. Pin drop silence. This is what the teachers in my school used to say. Sit down. Pin drop silence from Batman. Pin drop. Mark? Who's that? Who is that? Is that an actor? Pin drop silence. Oh. Doro, meet the newest troll. Manoj is here. Plumber is pronounced plumber. Plumber. No, I say plumber. Just like I say Connecticut, not Connecticut. I say Connecticut. Dora, please acquaint yourself with the newest troll in the chat. I was getting no playback on my TV. Now I'm getting playback on my big TV. What do you mean? Pin drop silence. Pin drop. Even a pin, when it drops, I should be able to hear it from Batman. Not Mark. You'll see. You'll see. Just give it a second. Just give it a second. Ooh, can we get 25 likes? In fact, can we get 30 likes? Oh, Marky Mark. Marky Mark is a good one. He's good. Marky Mark is not a troll. I meant somebody else. Oh, he was already timed out by Reese. Okay, so Reese timed this person out for 60 seconds. You should have seen some of the comments he's been leaving me. And also the stuff he said on some of my lives recently where you guys were not there. And I'm like, oh my God, where are my mods? I had to get my hands dirty myself. Mad Hatter, hello. Harper says, hi, Marky Mark, good job. When you came back, I could see you moving, but my TV had frozen, so I left and came back in. Oh, nice. You see me on the TV? Good. Oh, good. I have 25 likes. Can I get 30 likes? Can I get 30 likes? 30 likes? 30 likes? Marky Mark says, I'll fade him. Mad Hatter, where are you? Hello, what did I miss? Yes, I'll tell you. So we have been talking about comparative planetology and the origin of the solar system. I missed you. I have been gone for a few days. 30 likes and she will call the plumber from Connecticut. Why don't notify me when you go live? Well, I try. Is it not notifying you? Maybe hit the bell icon or whatever on YouTube. Why don't notify me? I hope that it's notifying you, certainly. Show us Baji. Oh, here. Baji, Baji. Shona Baji. That's Baji right there. Show us Baji. I'm okay. I see live streams better on my TV and can still type messages. That's Professor McGonagall. Yes! Marky Mark made this extremely good comment a few lives ago, and it was one of my favorite messages I've ever seen on the live, which is that Baji is Professor McGonagall. Shona. No, you keep quiet, Batman. Keep quiet. Keep on choosing silence and just listen. Just listen. Keep on choosing silence. I'm the professor from Gilligan's Island. Aww. Everybody. Okay. Thank you so much, everybody, for being here. Thank you, Doro. Thank you, Steven. Thank you, Harper. Marky Mark. Welcome. Reese. Reese has done an amazing job with the newest troll in town. Lots of prompt timeouts I see. Thank you, Mad Hatter. Thank you, Batman, for your silence. Okay, now we will talk about detecting exoplanets. So, as we do a thorough assessment and research of our own solar system and find all of the diversity and variety in our own solar system, of course, it is, helpful to learn about both the planet formation in this solar system and about all the different planets and the different compositions and environments they provide, and to note, well, where is relatively life being supported or not, and also sort of and also sort of when we see certain signatures. So keep in mind that when we see certain signatures of these exoplanets, we might have an ability to sort of compare, like this comparative planetology thing that we were just now doing. This actually applies to studies of exoplanets as well. When we see things and we're like, oh, is that planet kind of like Jupiter, the one we see sort of near, or the one we see as part of a different star system? Is that sort of like Jupiter, or is it sort of like Earth, or is it sort of like Neptune? Things like that. So, indeed, all of the things we learn about our own solar system is super helpful, but we will see some of the challenges and ways in a little bit here. In like 1 second. Yes, go get your cat. Okay. Yes, we're all cat lovers. I have a theory that people who have cats. Oh, thank you. There's Baji Baba. All right, so although astronomers have developed a broad outline of how the solar system formed, details are still lacking. One of the most active fields in astronomy is the study of exoplanets, or planets around stars other than the sun. So that's the definition of exoplanets, planets that are around stars other than our own sun. As more exoplanets are discovered, the statistical study of planetary systems will allow a better general understanding of how planets form and evolve, and whether our own solar system is ordinary or anomalous. So another thing too is we have this question, is our own solar system sort of a normal one, or is it an anomaly? Are we kind of special, or are we the usual? Like this sort of solar system we have, the big sun, then the smaller planets, Mercury, Venus, Earth, Mars, and then the bigger planets, Jupiter, Saturn, Uranus, Neptune. Is that sort of like a very ordinary, normal type of distribution and composition of the solar system, or is that kind of special? Because we know yeah. We know that this particular solar system, of course, hosts life, as in us. So we will see. Detecting planets around other stars is far more difficult than detecting planets orbiting the sun. So we will see why there are certain challenges actually for detecting these other planets around other stars, because of course, even detecting some of the planets in our own solar system was more challenging, but definitely a lot easier than the ones that are around other stars. Neptune is one that was discovered when it was close to opposition at around 29 astronomical units from the Earth. By comparison, the Sun's nearest neighbor among the stars, Proxima Centauri, is at a distance of around 270,000 astronomical units, which is around 1.3 parsecs from the Earth. To illustrate the difficulties involved in detecting exoplanets, let's imagine we are located at the position of Proxima Centauri and want to detect Jupiter as it orbits the Sun. So we're going to do this the other way around. Let's say we are at the position of Proxima Centauri, which is, of course, the closest star other than the Sun. And let's say that we're trying to detect the biggest planet in our solar system, which is Jupiter. So yeah, Proxima Centauri is at a distance of 270,000 astronomical units. And so since Jupiter is the largest planet in the solar system, of course, we expect it to be more easily detectable from Proxima Centauri. Jupiter is on a nearly circular orbit with a semi-major axis of 5.2 astronomical units. So we know that Jupiter is 5.2 astronomical units from the Sun. We are 1 astronomical units from the Sun, the Earth, and Jupiter is at around 5 astronomical units. Its maximum angular separation from the Sun as seen. So the thing is, when you're a very large distance away, it's really that angular separation between the Sun and Jupiter which will kind of matter a lot. So because from a long distance away, they might still seem kind of close together. And the angular separation we will calculate or have an estimate for. So its maximum angular separation from the Sun, as seen from a distance of that d of 270,000 astronomical units, will be theta given by small a over d, where the small a is the semi-major axis, 5.2 astronomical units, and the small d, hi Fuji, is the 270,000 astronomical units. So we're doing theta, which is equal to the angular separation, which is equal to the ratio of these two distances, 5.2 over 270,000. So you can see how that's going to be kind of small. Yeah, the small d is the distance from Proxima Centauri. And so this number, the angular separation number, which is the ratio of those two distances of being able to see Jupiter from a large distance away, in this case Proxima Centauri, which is of course the nearest star away from the nearest star other than the Sun, that number is 1.9 times 10 to the negative 5 radians. So converting from radians to arc seconds and scaling to an arbitrary orbit size small a at an arbitrary distance small d, we find that theta is equal to 4 arc seconds times a over 5.2 times d over 270,000 to the minus 1. Thus, in the diffraction limited case, a telescope with d, now let me make sure about this particular, oh, I see, diffraction limited case, let me see, 1 second, give me 1 second. Equation 6.7. Let me verify one thing. When it references an equation, if it says 6.7, we go to chapter 6 and look for equation 6.7, because I want to say what it is that I'm trying to. Fuji has cute beans. Thank you for being here, everybody. So before I tell you about this telescope equation, I need to define something. That's why I am looking for it right now. Okay, so we know the angular separation of Jupiter as viewed from Proxima Centauri. The next part has to do with a telescope equation. So I'm just looking for that particular spot so I can tell you about it. So here it is. So basically, if you have a telescope with an aperture size D, this is big D, and the wavelength lambda of the observed light, 2-point sources can be resolved as separate objects when the center of the airy disk of one source falls into the dark ring surrounding the airy disk of the other source. So this is all about if we're able to even see two things apart or not, okay? This happens when the centers of the two light sources are separated by a distance, theta min. So there is going to be a sort of a lower limit on the theta or the angular separation, which will be resolvable basically, and that's given by 1.22 lambda over big D. If we observe at visible wavelengths, this lambda is going to be around 5,000 angstroms, then resolving two stars separated by an angular distance theta of around 1 seconds, which is around 4.8 times 10 to the minus 6 radians, require a telescope of minimum diameter of 0.13 meters. So this aperture size of big D is associated with the telescope, okay? So that's what we're looking at here. We know the angular separation number for Jupiter as viewed from Proxima Centauri so the angular separation between Jupiter and the Sun as viewed from Proxima Centauri. So now let's see. In the diffraction limited case, a telescope with D of greater than 4 centimeters, this D is the aperture size of the telescope, would provide sufficient angular resolution. So this is what we're talking about, the angular resolution, is it possible or not, to distinguish Jupiter from the Sun. So if your telescope has an aperture size of more than 4 centimeters, it should be able to, would provide sufficient angular resolution to distinguish Jupiter from the Sun as seen from Proxima Centauri. Can we get 30 likes, please? In reality, the difficulty in detecting Jupiter would come not from its proximity to the Sun, but from its dimness relative to the Sun. So if you thought that that particular angular separation, which was only 1.9 times 10 to the negative 5 radians, was too small, can we resolve that or not? Well, even though it's small, the aperture size for the telescope here is not that big of a deal. It's not that impossible. We could do it, but actually Jupiter is a lot more dimmer than the Sun, and that is why it is going to be more of a challenge. So at visible wavelengths, so again, it depends which wavelength you look in, right? So it could be visible wavelength, some other type of light, etc. So let's say we're at Proxima Centauri and we're trying to look at Jupiter with visible wavelengths. So at visible wavelengths, Jupiter's luminosity is due to reflected sunlight, right? Because Jupiter might have an energy output at other wavelengths because of other things that we talked about. Remember, Jupiter actually has a very large energy output, but it might not be in the visible wavelength, right? So when it comes to visible wavelength, Jupiter's luminosity is mainly due to reflected sunlight. So of course that luminosity is going to be a lot lower than the luminosity of our Sun, which is the Sun, right? Like with its sunlight. So Jupiter's distance from the Sun is around, of course, 5.2 astronomical units, which is around 7.8 times 10 to the 8 kilometers. So again, 7.8 times 10 to the 8 kilometers. And its radius is around 11 times the radius of the Earth, which is around 7.2 times 10 to the 4 kilometers. And its albedo is A equal to 0.51. It's sort of a reflectivity type of thing. Its luminosity of reflected light is thus L Jupiter is equal to L Sun over 4 pi A squared times pi R Jupiter squared times big A, where A is the albedo, and all of that gives us a ratio of L Jupiter, as in the luminosity ratio of Jupiter over the sun, is around 4 times 10 to the negative 9. That's a very small number. So, of course, luminosity, again, of Jupiter at visible wavelengths is a lot less than the luminosity of the sun. So how do we calculate all the distances of the bodies from us? So depends on which bodies. We talked a little bit about how we know at what distances different stars are at, and one method was stellar parallax. I talked about this on Saturday for a little bit, actually, but I didn't finish talking about all the different ways in which you can get the distance of stars. It's actually a non-trivial topic, and we may talk about it in more detail in a different live. But yeah, that's a good question. If you're interested, you can go to the stellar parallax discussion that I did on Saturday. Yep. Yeah, it's not an easy thing. It's not just like you just know. No, with it's very difficult because stars are very much far away, right? Like, as you saw, Proxima Centauri is 270,000 astronomical units away. The sun is 1 astronomical units away from us. So you could see how the nearest star is very, very far. So it's not easy to get the distances, okay? But parallax is one of them. So if an object, so we know that the luminosity ratio is 4 times 10 to the minus 9 between Jupiter and the sun, where the sun is obviously more luminous. If an object with a luminosity L of around 4 times 10 to the minus 9 L sun were seen against a very dark background, it would be detectable from the distance of Proxima Centauri. However, the sun's image would provide a very bright background for the image of Jupiter. So it really depends, right? If you're looking at something and there's a very dim thing, and you see it against a very dark background, then it's more visible. But if you're seeing it against a very bright background, because the sun is right there, then it could be very, very difficult. So the sun's image would provide a bright background for the image of Jupiter, making the unambiguous detection of Jupiter's image far more difficult. So Sirius is Sirius, if that's what you mean, and Sirius is a binary. Yeah, so Sirius is actually a binary. We can talk about the Sirius system in just a little bit since you asked. Obviously, there's a lot of variables. Yeah, thank you for asking about Sirius. Thank you, and welcome, Kimmy, Ox, Secret. Hi, Kimmy, how are you? I think so. Sirius, is Sirius considered the brightest star or something? I don't think it, yeah, I'm not sure if it's considered the North Star. As you said, it might be Polaris, which is considered the North Star. But anyway, one way. So far, we kind of understand that Jupiter is kind of hard to see from Proxima Centauri. So the same thing, like we're trying to see other planets around other star systems, and that's not a trivial matter. As you can see, when we see Jupiter from Proxima Centauri, it's kind of dim and it's kind of really hard, but we'll figure it out. We'll keep going. One way we can increase the apparent brightness of Jupiter relative to the sun is to look for the thermal emission from Jupiter at photon energies h nu less than or equal to kT Jupiter. So there is this relationship between energy and temperature. Reese, you might find this interesting because I think you're asking about that. So h nu, the Planck's constant times the frequency of light, is that energy, and that energy is also equal to K Boltzmann, so the Boltzmann constant times temperature. So if we think of photon energies like this, and we think about the thermal emission of Jupiter, then we might have more luck. Let's see. Given Jupiter's temperature, so we know Jupiter's temperature, it is 150 kelvins. And we actually know that there is thermal emission from Jupiter, right? So let's see what frequency that is associated with. So given Jupiter's temperature of 150 kelvins, this implies a nu, or a frequency associated with that, of 3 times 10 to the 12 hertz, or the lambda associated with that frequency now is 100 microns. So basically, when something has a certain temperature, basically the energy associated with that thing is given by the relationship between temperature and the frequency, or the energy rather, is given by h nu equal to kt, where k is Boltzmann constant. So now, after we know that the temperature of Jupiter is 150 kelvins, we can convert this to a frequency, which is 3 times 10 to the 12 hertz, which if it's light, then we get the wavelength of that, which is 100 microns. So at these low frequencies, the emission from both Jupiter and the sun is in the Rayleigh-Jeans limit. Thus, the ratio of the specific flux of Jupiter. Thank you. I love hearing about physics. I need things explaining in layman terms. So we can talk about the Jupiter temperature at some point. We did kind of cover the... Oh, you're asking how do we figure out the temperature? we can definitely delve into that. Let's keep going for now. I love hearing about physics here and there. I feel comfortable here right now. Thanks for sharing educational information. Thank you, Kimmy. Thank you for being here. Love it. That's awesome. Yay. So there's this more math, a little bit more math here. There's a thing called Rayleigh-Jeans limit. Okay, so let's see if this is useful to cover here or not. There is a ratio of the specific flux of Jupiter to that of the sun, and once you put this together, it becomes independent of the frequency. We must also take into account the fact that the surface area of Jupiter is smaller than that of the sun. So approximating both Jupiter and the sun as spherical black bodies, because this thermal emission is basically sort of like a black body radiation. So we're saying, can we use this black body radiation of the Jupiter versus the sun to see something, to say something about their luminosity? So it's kind of like equivalent to the equivalent, as in the equation sign that's wavy, equivalent to T Jupiter over T sun for this black body type of radiation. And so as long the ratio of their specific luminosities, as long as we stay in the low frequency Rayleigh-Jeans limit, given that the radius of Jupiter is around 0.1 times the radius of the sun, and we also know the ratio of the temperature of Jupiter versus the sun, this implies, again, another new luminosity ratio of this other frequency, that is the thermal emission frequency. So we looked at the luminosity ratio in visible wavelength. The luminosity ratio for this thermal emission is a little bit better. So we saw the luminosity ratio in visible wavelength. If you really try to look at the luminosities of Jupiter and the sun in visible wavelength, that ratio was 4 times 10 to the negative 9. Very small number. In the thermal emission type of way, if you look at it, then that number is 3 times 10 to the negative 4. So that's a little better. 10 to the negative 4 is not bad. So by switching from visible light, which is lambda of around 0.5 microns, to far infrared light. So thermal emission is sort of in this far, what we call the far infrared light type of wavelengths. So the wavelengths are bigger, 100 microns or more. We increase the ratio of Jupiter light to sunlight from a tiny 4 times 10 to the negative 9 to a more respectable 3 times 10 to the negative 4. Hi, Fuji. So this is a trick or an approach that one might opt for because the thermal emission luminosity ratio is a lot better. The one from Jupiter. And actually, we talked about the big energy output of Jupiter. Remember when we covered Jupiter the other day? And we saw that because of Jupiter's contraction and compression under its own gravity, it actually releases gravitational potential energy in the form of this energy output. And basically, Jupiter does have a lot of energy output. And it turns out a lot of it is in this thermal emission, which is in the infrared light wavelength. And in that way, it has a lot of emission. And so its ratio with that of the sun is a lot better, more respectable, 3 times 10 to the negative 4, still a small number, but not as small as 4 times 10 to the negative 9, which is when we looked at it as visible wavelength. Because Jupiter's visible wavelength is, of course, whatever it's reflecting off of the sun. And nothing's going to be even close to the brightness of the sun. Yay! I love hearing it this way. Thank you. Welcome, everybody. Thank you so much. So, because direct imaging, this like taking a photograph basically of exoplanets, faraway planets, is going to be really tough because of these above mentioned reasons. So because direct imaging of exoplanets is difficult, planet searches have so far concentrated on indirect methods of finding exoplanets. So we're still kind of getting our bearings on how these things are even detected. Okay, and what are some ways? We talked about this visible wavelength thing. We saw what that would be kind of like. We talked about the thermal emission thing. Next, we will talk about a gravitational way. Okay, so because direct imaging of exoplanets is difficult, planet searchers have so far concentrated on indirect methods of finding exoplanets. For instance, the existence of a dim exoplanet can be deduced from its gravitational effect on its parent star. So this is yet another tool or tip or trick in our bag that we might use, which is even though the planets are, of course, a lot less massive than the stars, let's see if there is a deduction that we can make based on its gravitational effect on its parent star. Newton's law of universal gravitation tells us that the force exerted by Jupiter on the Sun, for instance, is equal in magnitude to the force exerted by the Sun on Jupiter. Thus, instead of saying Jupiter orbits the Sun, we should strictly say that both Jupiter and the Sun orbit the center of mass of the Jupiter-Sun system. Heck yes! The location of the center of mass of a two-body system can be readily calculated. So utilizing the the rotation, like the two things are basically rotating, strictly speaking, around each other, around the center of mass of the two body system. And we can observe what type of rotation is happening for those faraway planets, hopefully. Suppose that the two spherical objects, such as a star and a planet, are gravitationally bound to each other. The more massive object has a mass, ma, and the less massive object has a mass, mb. Yay! The two objects are separated by a distance, a. So then, the center of mass lies on the line segment connecting the centers of the two objects. If small a is the distance from ma to the center of mass, and ab is the distance from mb to the center of mass. So there's the two planets, then there's a center of mass, or sorry, there's the two objects, one planet, one sun. The center of mass, if this is the sun, it's going to be closer to this one, right? So these two distances are what we're talking about, AA and AB. So the center of mass is always closer to the more massive object. Yay! Exactly. To revert to our example of the Jupiter-Sun system, the mass of Jupiter is around 10 to the negative 3 mass of A, where mass A is one solar mass. Thus, as Jupiter travels on a large elliptical orbit with semi-major axis of 5.2 astronomical units, the Sun travels on a small elliptical orbit with semi-major axis 5.2 times 10 to the negative 3 astronomical units, or 1.1 radius of the Sun. As we computed above, the semi-major axis of Jupiter's orbit subtends an angle. So let me show you the picture, by the way. Here's the picture. It's just two round objects, and the center of mass is closer to the more massive object. That's the math that's going on here. So the semi-major axis of Jupiter's orbit subtends an angle of 4 arcseconds as seen from the distance of Proxima Centauri. So we saw that earlier, where we saw what the angular separation was as seen from Proxima Centauri. This implies that the semi-major axis of the Sun's orbit will subtend an angle of only 4 milliarcseconds. Generalizing, if a star of mass ma has an exoplanet of mass mb much less than ma, at a distance of a, the semi-major axis of the star's orbit will subtend an angle of all of this taken together, 0.004 arcseconds mb over ma, all over 0.001 times a over 5.2 times d over the 270,000 astronomical units to the -1. So it's sort of, we're taking that angular separation equation and putting in the values that we got here, where small d here is the distance from the observer to the star. So that small d, so we're taking the angular separation number or formula from the Proxima Centauri to Jupiter versus Sun and just generalizing it using the using these same things that we just talked about. So yeah, summarize it. So thus the angular size of the star's orbit is greatest for nearby stars with massive planets on large orbits. So if you're thinking about these angular sizes as seen from a different star, the stars, if the angular size of the star's orbit is greatest for nearby stars, so if it's not too far, then this angular separation will seem to be bigger. And also when they have massive planets on large orbits. So farther away or larger the orbit and more massive the star, because all these masses and semi-major axes are part of that equation. Okay, so if we were in the vicinity of Proxima Centauri discovering Jupiter by direct imaging, that is taking a snapshot of Jupiter, or by astrometry, it's like photography, but in astronomy, sort of. That is watching the sun trace out a small ellipse. We would face different technical difficulties. The orbit of Jupiter would be relatively large in angular size, a point in favor of direct imaging, but detecting Jupiter would be difficult because of its tiny luminosity compared to the sun. The sun itself would be simple to detect. The Mayans had it all sussed out. Oh, interesting. Which binary was it? Ooh, can I get 30 likes? So because of the difficulties involved in direct imaging and astrometry, most exoplanets discovered to date have been found using other techniques. Our solar system, I mean. What? Okay. So one such technique is the radial velocity. They knew the size of all the planets in proportion. Oh, really? Oh, I didn't know that. So one such technique is the radial velocity method. If the orbital velocity of a star caused by an unseen exoplanet. So we talked about the angular separation numbers, the taking a picture, all that stuff. Now we're talking about radial velocity method. So if the orbital velocity of a star caused by an unseen exoplanet has a component VR along the line of sight to an observer, it will cause a Doppler shift. Wow. Of delta lambda over lambda is equal to VR over C. In the absorption lines of the star's spectrum, it's almost like, why didn't you tell me about this first, authors? If they're astronomers, they're going to use some kind of absorption line thing. So, okay. Consider the simple case of a star with mass ma and a planet with mass mb on circular orbits about their center of mass, blah, blah, blah. The orbital periods of the star and planet about the center of the mass are identical. Oh. About the center of mass. Got it. Okay. So here you get VA over VB is equal to basically MB over MA. Again, using the Jupiter-Sun system as our example, because that's what we're considering, the orbital speed of the Sun will then be around 13 meters per second. What? Okay. Thus, the Sun's orbital speed is a modest 13 meters per second, or about 29 miles per hour. And so if you're able to, I guess, measure that, goodness. They knew about Series B. Oh, cool. Yeah. The binary. With current techniques, yeah, I looked it up. Good. That's good. With current techniques, the radial velocity of relatively bright stars can be determined to within 1 meters per second. Thus, it is technologically feasible to detect Jupiter-like exoplanets from their effect on the radial velocity of sun-like stars. So all of this was to say that if the planet is causing a radial velocity on its star, we are sensitive to something like, we can pick it up if it's something like 1 meters per second or above. So basically, if there's a Jupiter-like planet having an effect like this on a sun-like star, then we are probably sensitive to it. So suppose that we're looking at a system that consists of a star, and a single planet. So the thing is that the star could have multiple planets, right? So let's look at this example now that they're talking about single planet. The center of mass of the system will be moving with some radial velocity. In addition, if the star and the planet are on circular orbits and we are in the orbital plane of the system, the radial velocity of the star will show sinusoidal variations. So that's another nice thing, is that it'll change. The sinusoidal curve will have an amplitude VA and a period P equal to the orbital period of the planet. Thank God. In general, though, we will not be in the orbital plane of the system. We will be observing the orbital plane at an inclination, I. Orbital period of the planet. Yes, periodic. What did I say? So then, now we're viewing things at an inclination, blah, blah, blah. Oh, so that makes it so that measured amplitude of a radial velocity curve is only equal to VA if we are observing the orbital plane edge on, like this, and the I is 90 degrees for the sine I. Hi, Fuji. It's midnight, Fuji. Gift time. Hi, Fuji. Hi, baby. Hi, baby. Mama loves you. Mama loves you. Thank you. Thank you for the gift. I hope you find Oh, look at Baji. Look at Baji, Baba. Shona to, Shona. Hi, Sachi Mama. Sachi is looking directly at me. Hi. Hi, Fuji Suji Baji. Okay, so this sine I is going to be an interesting thing as well, okay? So from the velocity curve of a star with an unseen companion, we can determine the orbital period P and the value of VA sine I. Let's see how we can use these measured quantities to deduce the properties of the perturbing exoplanet. Hi, Fuji Shona. Come, beta. Come. You can sit on that book. I have prepared it for you. Fuji, come. Come, Fuji. So this VA sine I is gonna be important. Hi, Fuji. You can sit. Good job. Good job. So Kepler's third law, as modified by Newton, tells us that this AA plus AB to the third is G times MA plus MB P squared over 4 pi squared. That's Kepler's third law, which has to do with the orbital period and whatnot. And in the case that MA is much, much bigger than MB, which is pretty much the case with the star and the planet usually, there is some simplification and you get that AB to the third is around GMA P squared over 4 pi squared. The mass MA of the star can usually be deduced from its spectrum. So masses of stars we will see can be deduced from the spectrum. For instance, stars with spectra similar to the sun's have masses close to a solar mass. Knowledge of the star's mass enables us to estimate the size of the planet's orbit by using this Kepler's third law. In addition, the amplitude of the velocity curve, VA sine I, gives us some knowledge of the mass of the planet. Yes, using this relation, MA over MB times AA is equal to AB, we start doing more math and we eventually get that basically this MB, which is the mass of the planet, that's another detail. Unfortunately, so it all boils down to having an equation which relates MB with MAP, 2 pi G, and VA. Unfortunately, we can't really measure VA. We can measure only VA sin I. Because remember that inclination thing. We understand that we may not be looking at the orbital plane edge on. So really we're looking at VA. We can measure VA sin I. Thus, we can't compute MB. We can only compute MB sin I. So MB sin I is going to be approximately 11. Apparently the mass of the Earth is now a thing as well, because it comes from putting it in for, because remember Jupiter had some relationship with the mass of the Earth. Oh my God, are we gonna seriously do that? Why is... Wait a minute. Oh, wait a minute. VA, no. In the above equation, M Earth, well, we know the mass of the Earth is 6 times 10 to the 24 kilograms. It takes 318 Earths to equal the mass of 1 Jupiter. We did know that. We did know that. Oh, I think the 11 numbers actually come from there's an 11 in the equation now, which is fine. That comes from the radius, I believe. Jupiter's radius is like 11 times the radius of the Earth, whatever. So if an exoplanet is to be detected by the radial velocity method, if you're going to do it with this method, it must produce VA sin I large enough to measure. So we won't really know VA, but we will have some VA sin I. If VA sin I is large enough, we can measure it. So exoplanets whose orbits are more nearly edge on, where sin I would be around 1, are more readily detectable. In addition, since VA has a proportion, it's proportional to MB, MA to the negative 2/3, P to the minus 1/3 from the Kepler law stuff. Oh my gosh, Kepler's third law. Fuji, let's not bite that. Fuji? No.